Hello, today we're going to be talking about 10.2 and 10.3, our SWABAT. For the first lesson is to simplify radical expressions. And in order to do that, we're going to be kind of like reducing as if they were fractions, except we are reducing radicals instead. So in order to do that, we want to remind ourselves what the perfect squares are. Like, for example, 1 squared is 1, 2 squared is 4, 3 squared is 9, then 16, 25 for 5 squared. 6 squared is 36, 7 squared is 49, 64, I don't know, 81, 100, 121, and then so on, and so on. So remember these, because we've seen them before, but they kind of just will kind of keep coming back. So in order to reduce, we do need this property. So the square root of a times b is equal to the square root of a times the square root of b. So we can separate them out into two separate radicals once we get them broken down. So I'm looking at the number 48, and when I'm looking at 48, I'm trying to figure out what's the biggest number of all these perfect squares that goes into 48. So I start with 36, I would say, because it's the closest one without going over, and then I kind of just work my way to the left of it. So 36 does not go into that evenly because you'd have some remainders. 25, same situation. 16, though, does go into here evenly. You can check it in the calculator, but it's 16 times 3. So using the property, I can break that down to the square root of 16 times the square root of 3. The square root of 16 I know is 4. Square root of 3, I don't know. So I would leave that the same way. So the only thing I'm doing is taking out the perfect square. Let's try another one. So I like the number 49 because it's on my list and I know that I can take that out. But I'm looking at these as well, and I kind of want to write those as perfect squares the same way that I did for this 16. So the square root of 49, it's great. Actually, we can just take it out now. Square root of 49 is 7. And now I'm looking at the variables that we have here. And I want to break those down in perfect squares. So I know that a squared is a perfect square, because what's the square root of a squared? Just a. But a squared is not the same thing as a to the fourth. So how many more a squareds do I need? Well, now I have 1, 2, 3, 4, and I have that 4 now. So I'm going to look and try to do the same thing for each term. So now I have to the fifth. Well, I need to be perfect square, so that means I need b squared. I'm going to keep adding b squareds until I get to 5, except I have 1, 2, 3, 4, but I need one more to make it b to the fifth. So 1, 2, 3, 4, 5. Now I have my b to the fifth, and I'm good there. So you're breaking these down to see, like, okay, well, how many perfect ones do I actually have here? C to the ninth. Well, I know it's a c squared and another c squared. That's 1, 2, 3, 4. Not to 9 yet. C squared, 1, 2, 3, 4, 5, 6. C squared, 1, 2, 3, 4, 5, 6, 7, 8. Not quite 9. I need one more. That's not a perfect square, but that's okay. So now I'm looking at what can I actually take out of here. So the 7 is already out. That's done. And now I have 1, 2 perfect squares. 2. There's 1, 2. And there's no a's left over. Now what about the b's? I have 1, 2 perfect squares that are b's. So I'm going to take out b squared. Yeah, I miscounted. I'm going to fix that right now. Don't worry. Don't worry. There were 2 for the a's. There's 2 for the b's. And then what about those c's? 1, 2, 3, 4. So c to the fourth comes out. Now we did have some leftovers on the inside, just like right here we had the leftover 3. We have some leftovers, at least with the variables. So all the a's went out, but I do have, still have this b to the first power, because that was not a perfect square, so I still have that in there. And then 1, 2, 3, 4, the c's came out, but I still have this c left over. So this will be my final answer. If I could write it in one color, that'd be kind of cool. 7a squared, b squared, c to the fourth, all that came out, and then left over was just bc. So we'll do that when we do these, just to kind of let you see it and see how things are breaking down. Next thing I have is 150, and I'm looking for perfect squares yet again. So 150, kind of close to 121, that doesn't go in evenly, 81 does not go in evenly. So this is what I do literally in my head. And I check each one. Nope, nope, nope. 25 does though. 25 times what? Well, you can check it on your calculator. 25 times 6 gives you 150. And then I'm going to break down the m's again. So m squared, and then m, because there's 1, 2, 3, 4, 5 m's. Then for the n's, n squared, and then n. That gives me 1, 2, 3, 4, 5. Okay, now I like to take out my perfect squares if you don't mind. So the square root of 25. Well, what's the square root of 25? 25 is like 5 squared. So that comes out as just 5. And then I have 2 perfect squares that are m, so m squared, because there's 2 perfect ones. There's also 2 perfect n's, so n squared comes out as well. And then I have my leftovers, and I'm going to put those in the radical, or leave those in the radical. So I still had a 6, so that's still in there. I still see an m, and I still see an n. And that would be your final answer. Didn't really have enough space to write them all under their own radical like I did here and here, but I just wanted to show you that in the beginning so that you can see it. All right, keeping it pushing. Now they would like for me to simplify. Not really different because they wanted me to simplify before, but it looks a little bit different because there are already 2 separate ones, but they don't really work for me this way. So what I'm going to do is combine them first. And in order to combine them, one rule, you can only multiply what's inside with what's inside and what's outside with what's outside. So when I say that, what's inside, well, inside I have this and this. So 6 times, like this 1, would just be 6, my bad. Would just be 6. And then x squared times x. So if I have x cubed times x, then I have a total of x to the 4th. Because remember, when you're multiplying, you add the exponents. And then I also have y in there. Now that 3, kind of just hanging out by itself, it's outside. So I'm going to keep it outside. It's an outsider. But we're going to see if we can have some things join it in just a moment. So this 3, fine right there. I'm looking on the inside now, and I'm trying to figure out, okay, well, what are my perfect squares? Are there any? And if so, let's try to pull them out. So the 6 is nothing's perfect about that. So if you're looking at that list that you have from the previous one, none of that goes in there. But this x to the 4th, I can break down. It's x squared, and then another x squared, and then I don't have any left over because it's 1, 2, 3, 4. And then I have the y. So now, that 3 still out there hanging out, we're just going to rewrite that as our 3. And then on the inside, oh, just kidding. And then we had our 2x squareds, perfect squareds there, so 3x squared. And then left on the inside is still 6 and a y. All right, so let's try your next one if you don't mind. Even if you did, we're still going to do it. So remember what we just said. We can only multiply what's outside, so 7 and 3, and get 21. And then what's inside. So I have that 5b, and then I have 20b to the 5th. So 5 times 20 is 100, which I like because it's on my list. And then b times b to the 5th is b to the 6th, because remember, this is like 1 plus 5 gives you the 6. Well, let's kind of keep track of what we have and where we have it. So this 21 is still outside. I want to show you this a little bit more actually, so I'm going to expand it out. Kind of, you can do this in your head, but just in case. 100 is like 10 squared. B to the 6th is b, that's a b, squared times b squared times b squared. So now, what can I take out? Well, I'm going to go ahead and rewrite that 21 so that I don't forget it. And then coming out of the radical, 10 squared is just 10, so that's there. And then I have 1, 2, 3 perfect b's. So 21 times 10 gives me 210 b to the 3rd power. There you go. It was all perfect. That worked out really nicely. Okay, one more example in this section, and then we'll do part 2 video for 10.3. Here's our quotient property of radicals. The square root of a over b equals the square root of a times this over the square root of b. So just like for multiplication, we can kind of separate them out. So I'm looking at this, and that means I can make this the square root of 13 over the square root of 36. Square root of 13 does not, there's no perfect squares in this one. I went down the list in my head, trust me. And the square root of 36 is 6. And there you go for that one. Now number 7 looks like, well, what do you want me to do, Misfits? It looks kind of simplified right there already because it already has its own separate things. But I'm going to tell you, this is a problem for us. This is called irrational. It's not allowed, basically. So we're going to get rid of it. So you have to think about it. What do I have to multiply this by in order to make it cancel out? Well, in order for it to cancel out, it would be nice if this was just 5 squared on the bottom. So what can I multiply this by to make it 5 squared? I feel like I can multiply it by the square root of 5, because 5 times 5 is 5 squared, which is 25. And then these would cancel out because the square root of 25 is just 5. And I would not have a problem anymore. But we do have to remember that whatever I do to the denominator, I also need to do to the numerator. So I'm going to do that here as well. So now I have a new numerator. 2 times 5 is 10, and then x squared is still there. And so I'm looking at the square root of 10 x squared, and then you're looking at that x squared, hopefully, because you've developed your own alert system, and you're realizing this is a perfect square, so let's pull it out. That square root of 10, that 10 is still in there, and then I have a 5 in the denominator still. I'm boxing it. I cannot reduce these two because this is in the radical and this is not, so you can leave it just the way that it is right there. Okay, looking at your next and final example on this part, you have a couple, 2, 3 options. One thing I'm seeing right now, just like for the previous problem, where you can only multiply what's in the insides with what's in the insides and what's on the outsides with what's in the outsides, we could reduce this because this was inside and this was outside. But I'm now looking at this 24 and this 48, and I'm feeling like I could reduce that. I don't know if I want to or not, but I do. I think I'm going to try it and see if I can make the numbers a little bit stronger. Going off script here. So this 24 and this 48, well, 24 goes into there. So it's like having the square root of 1. If I divide this by 24, I'm trying to show my work, divide this by 24. So then I get 24 divided by 24 is 1. That's a nice friendly one because the square root of 1 is just 1. And then in the denominator, 48 divided by 24 is 2. And then I have, oh, this is going to be nice, m squared times m squared. Let's simplify a bit. So up top right now, we just said that the square root of 1 is 1. So I can kind of just ignore this. So 2 times 1, that's just 2. In the denominator, m squared times m squared, these are both perfect squares. I have 2 of them, so that's m squared will come out because there's 2 perfect squares in there. And then I just have the square root of 2 left on the inside. Now, same issue that I had before, I still have. I got a lot of issues, but that's okay. Don't judge me. Radical 2 in the denominator, not allowed. We're going to do one more step here. What would I have to multiply it by? Basically itself. Square root 2, square root 2. Let me show you how that worked. This is m squared times the square root of 2 squared over 2 times the square root of 2. Remember, these are not both inside. So one will stay outside, this one can stay inside. Okay, let's simplify a little more. This is 2 square root 2. You're going to love that we have more work to do. I have this m squared is still there. And what is the square root of 2 squared? Where these cancel out and I just have 2. We could reduce just a little bit more. These 2's go away. And I have the square root of 2 over m squared. It's a delicate problem. Probably one of the hardest ones you'll ever see in your life. All right. Thank you so much. Okay, probably not your life, but probably just in this class. And I will see you for the next lesson.